Okay, now you're going to see the power of this great theorem about all these little right triangles being similar to each other. And you'll also see the idea of a geometric mean naturally coming out and springing forth in various examples. So look at the power of this theorem. Suppose I'm given this right triangle here. This length is y, this length is z, and this entire length I guess we can figure out, but when we drop the altitude down, so this is a right angle, I'm told this is 3 and this is 8. So therefore the whole thing must be 11. Our mission, should we choose to accept it, is to find the lengths of the altitude and these two remaining sides, y and z. Now, it may sound as though we don't have enough information to actually do this, but it turns out if we use the theorem and the idea of the geometric mean, we can actually find these things. Why? Because the triangles are similar. That means that corresponding various ratios of corresponding parts are going to be equal. So let's set up some proportions. Well, let's see. Since this triangle right here, the large triangle, is similar to this small triangle, then corresponding ratios of corresponding parts are going to be equal. So for example, this, looking at the whole triangle here, this leg is to the hypotenuse, so that means that y is to the hypotenuse, 11, as, well, the little leg here is to the hypotenuse of this little triangle. So that means 3 is to y. Now, once I set up this proportion, you see, now I can use the cross product, and what do I discover? I discover that actually there's a geometric mean here, because this tells me, after I consider the cross product, that y squared equals 3 times 11. And so now y is an actual length, so in fact I can just take the positive square root, and so I see y equals the square root of 3 times 11. And what do I see? I see that y, in fact, is the geometric mean of 3 and 11. Isn't that cool? And so we see that y equals the square root of 33. And so I just found out that this length here is the square root of 33. That's awesome. That's awesome. Okay, so let's now try to find the other sides. So let's consider x. And again, we're going to see the geometric mean naturally showing up. So of course for x I use green. I don't know why. All right, so let's set up the ratio again. So let's see. So I've got this little triangle right here, this little right triangle, and I'm going to actually now compare it to this triangle right here. We know they're similar, so ratios of corresponding parts are going to be equal. We can set up a proportion. So this is the larger leg. This is the larger leg of the little triangle here. So the larger leg is to the smaller leg. The larger leg is to the smaller leg as, now look at here, the larger leg is to the smaller leg. So 8 over x. And when I take the cross product, look what happens. I'm beginning to see again a geometric mean. I'm taking the positive square root since x is a length, and I see x in fact is the geometric mean of 3 and 8. And so what do I see here? Well, you can simplify this a little bit, I guess, because 8 is actually 4 times 2. The square root of 4 is 2, and so this is going to actually equal 2 square root, and what do I have left under the radical? I've got the 3 and then the extra factor of 2, so that's going to be a 6. Neat. So this is going to be 2 square root of 6. And what about the z? Okay, no problem. Let's take a look at the z. Well, again, we're in the habit of this. We know it's going to be some kind of interesting mean, and let's see what kind of mean it's going to be. Well, in fact, this one's going to work out quite nicely because so many numbers are already known that I'm in great shape, because what I can say here is the following. I can say that the hypotenuse of this little teeny triangle is to the little teeny side, as the hypotenuse of this is to the little teeny side here. And so what I see here is square root of 33 is to 3. Little hypotenuse is to tiny side as, hypotenuse is to tiny side as hypotenuse is to tiny side. See, I'm setting up this proportion. And now we have to solve this, and we use the cross product. And now it's going to get a little bit complicated. I don't want to spend a lot of time on this. 3z equals, and on this side I see 2 square root of 6 times square root of 33. And you can simplify that a little bit, and you can simplify that down when you solve that to see that z equals, in fact, 2 square root of 22. So there's z, there's x, and there's y. And they all followed by just realizing this theorem that all the triangles are in fact similar, and in fact we're seeing lots of geometric means hidden. Pretty neat.